Consider the exponential distribution. The continuous random variable x as an exponential distribution with parameter beta if its density function is given by this function. We observe that it is non-zero whenever x is greater than 0 and 0 otherwise, where beta is greater than 0. For such a distribution, the mean and variance are beta and beta square, and hence the standard deviation is beta. Let us consider a problem. Let the mileage of a particular tire be a random variable x having PDF defined by this. We need to find the probability that one of these tires will last at most 10,000 miles, anywhere between 16 to 24,000 miles, mean and variance. Here, by comparing this PDF with exponential PDF, we observed that beta is equal to 20. In order to tackle the first subdivision, here we need to find the probability that one of these tests will last at most 10,000. That is probability of finding x less than or equal to 10,000. In order to simplify the process of integration, we consider this as probability of x less than or equal to 10. And proceeding this, we have integral x from 0 to 10 f of x dx. By substituting f of x and integrating, we get the answer as this. Next, in order to consider the second subdivision, we see that x lies between 16 and 24. Therefore, that must be the limit of integration. By substituting f of x, we get the desired result as 0.148. And mean and variance are beta and beta square, which is 20 and 400. Next problem. Suppose that a system contains a certain type of component whose time in years to failure is given by t. The random variable t is modeled nicely by exponential distribution with the mean time of failure beta equal to 5. If 5 of these components are installed in different systems, what is the probability that at least 2 are still functioning at the end of 8 years? So here a situation is modeled by an exponential distribution. Therefore, we have f of x defined in two intervals when x is greater than 0 and when x is less than 0, and they have given beta equal to 5. So let us make note of it. So here we consider the random variable as t, and first we wish to find out the components that are still working at the end of 8 years as probability of t greater than 8, which is integral from 0 to 8 f of t dt. F of t is 1 over 5 e power minus t by 5, and integrating that results into 0.2. The next part of the problem is different, where we see that if 5 out of these components are installed in different systems, what is the probability that at least 2 are still functioning at the end of 8 years? So here the random variable x is not continuous, it is discrete. So therefore, I consider x representing the number of components functioning after 8 years, and I use the binomial distribution as there are only two outcomes. and therefore probability of getting x greater than or equal to 2, at least 2, is equal to the CDF of the binomial distribution with n equal to 5 because of this, and the mean is 0.2. So the same can be easily evaluated by considering the other way. So the total probability minus the binomial distribution x less than or equal to 1 is obtained after expanding this summation and evaluating it as 0.2627. Thank you.